Hi everybody, I'm going to continue with our discussion on the electromagnetic spectrum and applications. I'm going to pick up where we left off with infrared, talk about that briefly, and then move on to the short wavelengths, the ones shorter than visible light. I'm starting with this slide. I know I showed you some of the infrared stuff earlier because I think it's so important. It's associated with the greenhouse effect, which is crucial to climate change and global warming. So it's a conceptual one which we'll look into more mathematically later in the year. So what we understand is what gets in from the sun over here is visible light. In the atmosphere, some is absorbed and reflected, but a good chunk of it, roughly 70%, makes it to the Earth. And here it's absorbed. And the Earth warms as a consequence. So when it warms, as anything that's warm or has temperature, it must radiate energy. And the type of energy it radiates depends on its temperature. Since the Earth is going to be much cooler than the sun, so whereas the sun might be 6,000 Kelvin, the Earth is going to be only roughly 300 Kelvin. And because of that, it's going to radiate in the infrared part of the spectrum. And so infrared radiation travels through oxygen and N2 very easily, but it is affected by any gas that has more than 3 molecules, so especially CO2, CH4, and surprisingly, people don't realize this, water vapor is a very good greenhouse effect, or greenhouse gas. So because these molecules have natural frequencies that overlap that of infrared, they will absorb it. And when they absorb it, they have to get rid of it. They just can't keep getting warmer and warmer. So what they do is they re-radiate it in all directions, and a good chunk of it's re-radiated back to the Earth. So the Earth gets an additional amount of energy that will otherwise have escaped to space, so our eventual equilibrium temperature will be something higher than we would expect. And we'll eventually learn this has actually been a very important and good effect for most of civilization, but the Earth's history, but now we're taking it a little bit above and beyond what we're used to. Okay, so let's turn our attention to ultraviolet. So we skipped over visible because we'll discuss that in more detail with colors, and we've already talked about visible light, implicit in refraction, optics, etc. So what we understand about ultraviolet, as the name implies, is a wavelength that's just shorter than violet. Okay, it is put out by the sun in a decent amount, and our atmosphere blocks most ultraviolet, which we know, and that's where the ozone layer is very important. However, ultraviolet does get through the atmosphere, and it is associated with, in this case, tanning, right? Now, these are tanning beds. So if you go to a tanning bed, then you're exposing yourself to not only visible, but that's, you can see the visible light right here, but there's ultraviolet in there that you can't see. If you ever looked at a black light, and if I have time, I'll show you in class, that also has a decent amount of ultraviolet. So ultraviolet has a high enough energy that it can affect the pigment skin cells in your skin, the melanin. So it's associated with tanning, sunburn, and generally too much of it's not good. I think we know that. And so the extreme case of that is melanoma. And melanoma used to be an old person's disease. And as you're exposed to the sun over 5, 6, 7, 8 decades, you can get this skin cancer. It looks pretty gross. And oftentimes it's benign. Other times it can be so advanced that it can create issues and even be terminal. So generally you want to avoid ultraviolet. In hospitals, they use it for sterilization of instruments. It's very effective in killing viruses and bacteria where you don't have to rely on antibiotics or other chemicals. In the animal world, ultraviolet has its use since the sun inputs it. So to our eye, we look at this flower, it looks pretty yellowish, orangish. To a bee's eye, it looks different because when a bee looks at it in the ultraviolet, it helps the bee locate what it's looking for, generally pollen. So there are certain animals, especially bees and other insects, that are sensitive to the ultraviolet part of the spectrum. All right, so let's turn to next X-rays. X-rays are just even shorter forms of wavelength, okay? And X-rays have the ability to penetrate soft tissue, so that's why we use them to look at teeth, look at bones, etc. In astronomy, in the bottom right-hand view, X-rays are associated with, amongst other things, the indirect detection of black holes. So if we think there's a black hole in a certain part of the sky where you, by definition, can't see a black hole, we often look for very strong X-ray sources, because what's happening is often that black hole is surrounded by a companion star, and it's pulling material off that companion star. And that material swirls around and around that black hole, and because those are ions, the plasma from that star, they're charged, and anytime you make charged particles go around and around, they're accelerating, you must get radiation. That's the ultimate origin of radiation. And so this is such high energy that it glows in the X-rays. So when we see sources of X-rays in the sky with no visible counterpart, we're pretty sure there's a black hole there. And that's how the first ones were really discovered in the, I believe, 70s. Okay, lastly, we have gamma radiation. So gamma radiation is what most people think about when they hear radiation. They think, oh, that's bad. Okay? Gamma radiation is what very often you get from a nuclear blast. It's associated with nuclear processes. And in our lives, for most people, at least my generation, a little older, that's the nuclear age, which has generally been a very negative type of reputation, a connotation to it. So if you are unfortunate enough to be near a blast and you don't get wiped out by the shock wave, whatever, the radiation that comes out is highly intensive in gamma radiation. It can lead to severe acute cancer, death, or long-term mutations that will affect generations down the road. This is associated with the nuclear test blasts of the 50s and 60s, and then more in the recent future with accidents that occur in nuclear power plants. If you watch the miniseries Chernobyl, you can see how horrific exposure to gamma radiation is, and you never know it because you can't see it. On the positive side, gamma radiation is actually pretty important in medical imaging when X-rays won't do. So some of you may have had this happen. I know this, my daughter had to do this when she was young. Is what you can do is you can swallow a dye that has a radioactive material in it, and so when that dye circulates through your body, it will glow. You will be glowing very faintly in gamma radiation. So if you have a gamma scope, you can look at your skeleton and your tissue, and you can see features in it that you otherwise can't see with X-rays. So it has an interesting application in medical. The more obvious medical application is targeting cancer cells. If you have certain cancer, you can put little radioactive buttons that emit gamma radiation with the idea of targeting the cancerous cells and not, hopefully, too much of your healthy cells. Okay, so I'm going to finish with a video. I don't know how this will work videoing it, but when you look at the universe in gamma rays, it actually is pretty interesting. So what you see is this in the middle here, this looks like fire, is our center of our galaxy. And those dots, those green dots that are above and below, are certain gamma ray sources. So I'm going to finish this video here with a minute physics. Let's see how that works. We'll skip the ad in a second, and I will.
Why is the sky dark at night? You might think the answer is obvious. The sun isn't dark. But the only reason the sky looks blue during the day is that sunlight scatters off of the atmosphere. If we didn't have an atmosphere like on the moon, the sky would always be dark, even when the sun is shining. So let's rephrase the question. Why is space dark? I mean, space is full of stars. Countless stars which are all about as bright as the sun. And in an infinite eternal universe, no matter what direction you face, if you look far enough in that direction, you would see a star or galaxy. So the whole sky should be as bright as the sun, night and day. And since it's not, does the darkness of the night sky mean that there's some distance away from us when stars and galaxies just have a boundary between something and nothing? An edge to the universe? Not exactly. All of our evidence seems to indicate that space has no edge, but the universe itself does. Not a spatial edge, but a temporal one. As far as we know, the universe had a beginning, or at least a time about 13.7 billion years ago, when the universe was so small and crumbled up in itself, there was better notion of space and time. It's down. And since only a finite amount of time has passed since this so-called beginning, that means that some of the stars necessary to fill up with brightness in every direction are so far away that light from them haven't had time to reach us yet. It's as if the universe were a big thunderstorm, and we're still waiting to hear the thunder from the very distant stars. But wait, it's better. Since light takes time to travel across the universe, when we point our telescopes at something really far away, we're actually seeing that part of the universe look at the 2.5 billion-year-old light, it's not that we don't see stars just because the light from them hasn't gotten to us yet. We don't see any stars because we're getting a peek at the universe before any stars have formed. A starless universe. Now that sounds to me like a pretty good reason why we look up and see a dark night sky. But it's not. I mean, it is true that we can find points in the sky where there aren't any stars by looking past the earliest stars and thus farther back in time. But even when we point our telescopes past the earliest stars, we still see light. Not starlight, but the light left over from the Big Bang. We detect this cosmic background radiation coming more or less evenly from all directions, forming a background beyond the stars. So I guess the night sky isn't actually dark to begin with. Right. So if our telescopes tell us that the night sky isn't dark, then why does it look dark? Here's a clue to the real answer. When the Hubble telescope photographed the distant stars of the astoundingly beautiful Hubble Extreme Deep Field, it took the picture using an infrared camera. Why? Well, distant stars and galaxies are moving away from us because the universe is expanding. So the same way a record slowing down lowers the picture quality, the Doppler effect causes stars moving away from us to become red. And the farther away they are, the faster they move away from us and the redder they become, until they become infrared. And then we can't see them anymore, at least not with our human eyes. And that's why the night sky is dark. In summary, if we lived in an infinite, unchanging universe, the entire sky would be as bright as the sun. But the sky is dark at night, both because the universe had a beginning, so there aren't stars in every direction, and more importantly, because the light from super distant stars and the even more distant cosmic background radiation gets redshifted away from the visible spectrum by the expansion of the universe. So we just plain can't see it. Finally, we've shed some light on why the night sky is dark, and why it isn't.
All right, so that's a pretty good summary, I think, especially relating back to infrared and even the CMB, the microwave part of the background. So if you have any questions, as you know, come to class and we'll clarify.